for your okay, yeah. Thanks, Justin, for your introduction, and thanks everyone for joining us today. Today I'm gonna talk about this my humble experience about working both in theory and practice, and I'm gonna actually play my video recording of the talk. So please enjoy.
Yeah,
Okay,
so
yeah, thanks. This is Ichiro Hasuo. Sorry, I should just a moment. Sorry. Thanks. Yeah, yeah. This should work. Yeah. Okay.
yeah,
Okay.
so please.
Yeah. Thanks. This is Ichiro Hasuo at National Institute of Informatics and Sokendai, Tokyo, Japan. I'm honored to be invited as a speaker here, and today I'm gonna tell you about my humble experience about collaboration between theory and practice, theoretical studies and applicational studies. Hence the title: Think abstractly, work concretely. Yeah, so we are in the programming language theory, and in my opinion, this is one of the many fields that lies precisely in between theory and practice, right? So for us in such a position, the best case scenario will be this upward spiral between theoretical research and practical challenges. And from left to right here, theoretical research would provide solutions to practical challenges, real-world challenges, especially theoretical answers, theoretical solutions. They tend to be long-range ones and fundamental ones, bringing some benefits that others wouldn't imagine, right? So that's the power of theory. And on the other way, from practice to theory, what it can provide is questions. So practical challenges basically guide high-level research directions in theoretical research, providing questions. And otherwise, this theoretical research wouldn't be a sound one. But there are threats to this upward spiral between theory and practice, such as one, these solutions may not be effective ones. These questions, they may not be interesting ones from theoretical point of view. And there is always a communication barrier between theoreticians and practitioners. And there's another threat that is challenge that is different styles of research, while where theoreticians, they tend to work in smaller teams or even by themselves alone. In contrast, practitioners, they tend to work in bigger teams, right? And so this is the ideal situation, the upward spiral, reciprocal benefits between theory and practice. And this is some of my humble experience. So I started out as a researcher in categorical modeling, categorical theory of coalgebras. Basically, these are categorical representation of automata and state-based transition systems. And then this has led to some applications in security and privacy. And then proof automation was needed. And then we, yes, combined coalgebras with some automated gave us some results in probabilistic verification, such as linear programming-based algorithms, martingale type witnesses. But then this probabilistic verification naturally extends to much bigger context of cyber physical systems. Then this question uh, urged us to work on this particular topic that I'm gonna speak about later. And then there are some more challenges, lack of models that I'm gonna also spend time on later. We are basically here now, and now we are looking at their applications in automated driving and reliability, safety of machine learning systems. So like this is my humble experience, but today a big part of my talk will be spent on this particular work, non-standard analysis and formal verification. So this is, I chose this topic because it exemplifies the theoretical fun when we try to do new application. But it also uh, highlights some fundamental challenges that we are facing in the programming language research in 2020s. So that's something that I'm going to talk about too. Okay, so let's move on to the second part. That is this line of work as an example. This is a line of work that we did quite some time ago. But in a nutshell, it is about program logic transferred from programs to hybrid dynamics. And then this transfer is literal, literally as it is. Okay, so this is the target domain that many of you probably know. It's called hybrid systems. So unlike conventional software or programs, it combines, so it's not simply a discrete dynamics, it combines discrete and continuous dynamics, that is discrete jump and continuous flow. So which typically occurs when you throw in digital control in a physical environment. And this is one important aspect of cyber physical systems. For example, there's this event called CPS IoT Week done every year, and it consists of 4 or 5 main conferences and other workshops. But one of the main conferences is this HSCC Hybrid Systems Computational Control. Okay, and since this hybrid system combines jump and flow, there are 2 approaches: formal verification that conventionally deals with jumps, and control theory that conventionally deals with flows. Then, so like for us, coming from the formal verification background, the question is how to incorporate flows, right? And we want to do so with minimal cost practically, and also, I mean, in terms of theoretical efforts. And then, as you can imagine, many formal verification approaches, they include differential equations explicitly, such as in hybrid automata and differential dynamic logic. So this results in acute distinction between jumps and flows in these formalisms, right? Which is, of course, and these are natural approaches, and these are also successful approaches. But then in this line of work, we did it rather differently. And the slogan is we turned flow into jumps. So like in our framework, there's no flows, only jumps. So like an example is this one, where dt is a constant that stands for an infinitesimal number, infinitely small number. So then you can, so this is a strange program, right? So it looks benign. It's a usual program with a while loop, but there's this infinitesimal constant. So then you can imagine its execution. So like this is a small number. So in each iteration of this while loop, the value of t grows infinitesimally, grows gradually until it reaches 1. But then how many loop iterations we are looking at? It's infinitely many, right? Because dt is infinitely small. And that's, I mean, in a sense, this is an infinite loop, something that we try not to think about something that we try to avoid when we do programming, right? So this program, this modeling looks kind of natural, but if we think about its semantics, there are a lot of questions to be answered. And we found out in this work that non-standard analysis, non-standard technique, but quite established coming from 60s, this mathematical body of results, this provides a solid mathematical foundation to think about such modeling. Okay. So the framework that I'm showing today is this most basic one in our line of work. We take this usual framework of an imperative programming language, first order assertion language, and then Hoa style program logic. And we augment each of these with this infinitesimal constant dt. And then we show that we can define rigorous semantics by non-standard analysis. And main results are that this Hoa dt, the logic, is sound and relatively complete. So that is as good as the original Hoa logic. So this way, we can do program verification or static analysis of hybrid systems as if there is no continuous flow dynamics. Everything is jump. Yeah, okay, so non-standard analysis, I'm gonna spend a few minutes on it. So it's analysis, it's analysis formulated with this explicit occurrence of infinitesimal values. It's infinitely small. And so then like, this is sort of intuitive in the sense that, for example, the notion of continuity of functions, you can define in such a straightforward manner. If the input fluctuates only infinitesimally, then the output also fluctuates only infinitesimally. But then, so this is intuitive, and this is how Leibniz originally formulated analysis. But it's not hard to see that this easily leads to contradiction, because let's say that delta is an infinitesimal, right? But then what about half of delta? It's smaller than delta, right? So therefore, delta is not smaller than any positive real. So contradiction is easy. So we need to be careful in making such arguments. And in 1960s, Robinson, a model theorist, he found logical solid foundation using ultrafilters. So I'm gonna show basics of this non-standard analysis. We speak about hyper-real numbers, and it is a hyper-real number is a sequence of infinite sequence of real numbers modulo certain equivalence, but let's ignore this equivalence for the time being. So hyper-real numbers for now is an infinite sequence of real numbers. And on this set, we introduce operations section-wise. By the way, we call each element a section. So operations are section-wise, adding each section, for example, right? And then usual real numbers, they are hyper-real numbers by this embedding constant strings, constant sequence. And then what is the most interesting is predicates. So for example, if this hyper-real number is smaller than this hyper-real number, we decided section-wise this way, like comparing each section. But here we say for almost every section. And then a precise definition of this for almost every I comes later using ultrafilter. But for the time being, this sufficient condition is enough. This sufficient condition says that like for almost every I means for all indices for all sections except for finitely many. This is the usual meaning of this for almost every in analysis, right? We can also say for sufficiently large I or except for finitely many I. So this is a sufficient condition that you can remember now. Yeah, but then using this definition of predicates, we can show that there does exist an infinitesimal. For example, this one, hyper-real number represented by this decreasing sequence. It is infinitesimal in the sense that it is smaller than any positive real. Really? Let's compare this guy with any positive real, let's say 1 over n, right? But then here the key is that hyper-reals and usual reals, they are different, and the usual reals are represented by this constant sequence. So if we compare all these sections, then for the first finitely many sections, for the first n sections, this inequality doesn't hold. But after that, it keeps holding. So this inequality holds for almost every section. Therefore, it holds between these two hyperreals. Okay. And in a similar manner, we can show that this hyperreal number is an infinite number in the sense that it is bigger than any standard real number. Yeah, but then here is a trouble. So I said that the hyperreal is an infinite sequence of real numbers, right? So this is a hyperreal number. But then is it positive or equal to 0 or negative? And we want one of these to hold, right? Like, for example, because it's convenient if hyperreals are totally ordered. So we need one of these to hold, but which one? So here what we do, what we do in non-standard analysis is to extend the meaning of for almost every I in such a way that for each subset of this indices, the set of indices, either itself or its complement is almost all. And this is done by, if you are a logician, then you are probably very familiar with this notion. This is done by ultrafilter, something that we ignored before. So some basic theory about ultrafilters. Yeah, so an ultrafilter is a class of subsets, right? And then basically it's like an oracle that says for given subset X of natural numbers, this oracle says, yes, it is almost all, or no, it is not almost all. And this here are some axiomatics. An ultra filter, yes, this is what I said in the previous slide, for each x, either x itself or its complement, exactly one of them is almost all. And axiom number 2, if x and y are both almost all, then their intersection is almost all again. Number item condition 3, almost all is upward closed. And number 4, empty set is not almost all, which is sort of intuitive, natural, right? Okay. And then definition, a filter, not ultra, but filter is something that satisfies only these 3 conditions, 2, 3, 4, not 1. And then there's this cofinite or Frechet filter, which embodies the meaning of the usual the usual meaning of almost all, right? So if it is cofinite, then it is almost all. This is something that we can easily accept, right? But then here is consequence of Zone's lemma, the axiom choice. Any filter can be extended to an ultra, maximal ultra filter. Therefore, there exists an ultra filter that extends this cofinite filter, and this is what we use. Okay, but like what exactly this f is, like is choice. Okay, yeah. So then this ultra filter appears here, and then the precise definition of this inequality is that like okay, so this inequality holds for almost every section in this ultra filter sense. So this is the proper definition, and what follows is this remarkable property. It's it's the central theorem in non-standard analysis. It is called the transfer principle. It says that so the validity of a formula it doesn't change in reals or in hyperreals. Okay, in reals or hyperreals, the same first order theory, they have the same first order theory, modulo this so-called star transform, but the star transform is just like, it says that all quantifiers, they have to be on the, over the whole hyperreal space. So yes, like this, in short, the reals and the hyperreals, they are logically the same. Okay, so this is non-standard analysis. And now using that, I'm gonna introduce the semantics of these guys. So by the way, like let me start with the syntax. So while DT, it is the usual imperative language with while loops, but the only difference is that we have got this special constant DT that would stand for an infinitesimal number. Okay, and then the assertion language, it's the same as the usual first order language, but we restrict the, I mean, so like as in the transfer principle, we restrict the quantifiers to the starred ones. They range over hypernumbers. This is as usual in non-standard analysis. And then for the whole logic rules, we are looking at the literally the same rules as usual. And then by defining the semantics of these guys using non-standard analysis, we could prove that the whole logic here, they are sound and relatively complete. The 2 properties that the original whole logic also satisfies. Okay, but then, okay, let me introduce the semantics of these programs by illustration first. So the challenge is this one. So yeah, so this program, as I said, since this DT is infinitesimal, the while loop executes infinitely many times, right? But then somehow we expect that the semantics, I mean, after the execution, the value of T will be almost 1, like 1, basically. Here, it also runs, I mean, the loop executes infinitely many times, but here we expect the semantics to be divergence, bottom, right? So we are looking at 2 different infinite loops, and we should distinguish them. How can we do that? And then the idea is what we call section-wise execution. Yeah, so here's the idea. So look at this program, and then we are looking at some real numbers and hyper-real numbers. So the first thing we do is to expand them into sequences like this. No? And then not only that, we decompose the program itself into sections like this. Okay, but then once we do so, then each section is the usual program, right? There's no infinitesimals, there's no hyperreal. We only look at real numbers. So their semantics is well defined. And in this case, we can see that, for example, here the loop executes 3 times and the t becomes 1 eventually, right? So and in each section, the answer, the value of t is 1, yeah, which we get. And this is why the semantics of this program with infinitesimal here is that t is 1 after the execution. Okay, let's try this one, which is slightly different from the previous one.
My camera is off, so don't worry.
So we find these hyperreal numbers, expand them, expand them into sequences, and we break up the program itself into sections, and we execute them section-wise in each section. Then in this case, these are the results, and we bundle them up. And what we are seeing is this is 1 and this is dt, right? 1 plus dt, and which is what we would intuitively expect. What about this one? We want this program to diverge. It's easy. I think you can already picture it. The numbers are expanded into sequences, and the program itself is expanded into sequences, sections, and we execute section-wise. But in each section, this is while true, therefore they all diverge. Therefore, if we bundle up, we are looking at an infinite sequence of divergence, therefore divergence. Okay, and then to make it precise, this is the definition. It's like, so you see that like almost all clauses are the same as usual, except for the while loop, which says that, yeah, so first the program should be split up into sections, where a section is defined as follows. So each occurrence of dt is replaced with this real number. And then it is applied to the section of a memory state, and we do so for every I for each section, and then we bundle the result up. Okay. So yeah, like I mean, section, like taking section simply replaces dt with these section real numbers. Okay, and then there are some like nice structural properties that we can prove. We call them section-wise lemmas. So this section-wise execution lemma says that although this section-wise execution is only here in the definition, we can expand this section-wise execution to the whole language. The semantics is defined in such a way, and section-wise satisfaction is that sigma is a hyperstate with hyper-real numbers in them, and then phi is an assertion language formula. They are, I mean, their truth is determined by section-wise in this way for almost, like saying for almost every I. If you know the non-standard analysis, this is nothing but Walsh's theorem. Yeah, then we can also prove the same for Hoa triples. So this Hoa triple, speaking about hyperreal numbers, it is valid if and only if its sections are valid for almost all I in the ultra-filter sense. And this actually works as an interface for transferring various static analysis techniques such as invariant generation, abstract interpretation. Those techniques, like they can be transferred via this lemma. Okay, so an oft asked question is a while dt program executable? And the answer is not exactly, because it is a modeling language, right? So if once you get a while loop in this while dt, this loop typically executes infinitely many times. So it's a modeling language, definitely, but its advantage is that it is close to a common programming style of imperative programming. We also did some first order functional programming in our POPL 13 paper. And but then, so in any case, what we do with these programs, that is like you saw the Hoa logic, like static analysis by Hoa logic, right? And like, what we do with these programs is, after all, static analysis, and this means that we don't have to execute these programs. So we cannot execute these programs, but that's okay. We just do static analysis on them. Okay, so let me summarize what I've shown you. Non-standard analysis. This is a body of results from model theory, ultra filter, and so on. Transfer principle, Washer's theorem. Like I would put it as follows: the same logical language, in this case, the first order predicate logic. The same logical language interpreted in different models, reals and hyper reals, and in this case, the validity coincides. That's the transfer principle, right? And okay, on top of this non-standard analysis, we built our line of work. This is in brief, it is the transfer principle for denotational semantics and Hoa logic. And we showed that basically this transfer principle is still valid for the Hoa logic. But then we did so with application to hybrid dynamics, cyber physical systems in our mind. And we showed that logical verification techniques can be transferred in this literal sense too, like invariant generation and abstract interpretation. Okay, so this concludes the example technical part of the talk. And now I'm gonna talk a bit of some high-level lessons that I learned from this line of work and also from my experience of combining theory and practice. There are two messages. One is for model-based to model-free and the power of logic therein. And the second one is the title of this talk. Okay, so first I want to give credit to my collaborator, Kohei Suenaga. He works at Kyoto University in Japan, a programming language researcher. He's a guy with 10,000 wild ideas. And basically, so this idea of using non-standard analysis for hybrid systems, this is brought by him. And I remember him coming to me saying that, like, Ichiro, hey, we should do CPS. It's a rich field. And he was also saying that from his industry experience, that so industry guys working on CPS, like cars and so on. This was before the trend of automated driving. Still, he knew that these CPS people, they need help from programming language theory, formal methods, formal verification. And so in this experience, this is basically my history of my research portfolio. This work was an important turning point to me because it opened up my eyes to the rich field of cyber physical systems. And then after working on this line, these results, I thought that yes, like it's good. So the cyber physical systems, they are really important and interesting to us because there's this discrete continuous barrier, right? So programs are discrete dynamics, while cyber physical systems, they usually include continuous dynamics too. This discrete continuous barrier can be overcome by theory's abstraction power. That's what I thought. And indeed, in this line of work, we did so by via the power of logic, right? So model theory, non-standard analysis. But we could also we can also do various transfer from discrete continuous via category theory coalgebras. That's something that I learned in these lines of work. So so this abstraction, using abstraction to transfer results from software programs to cyber physical systems. This is one schematics that I can draw. So like we start with an existing technique such as Hoa logic for programs, right? The usual Hoa logic for programs. And then we look at the existing technique with our theoreticians' abstract eyes. So we try to identify the mathematical essences, then we get an abstract technique. Well, like in this case, it was the Hoa logic, it's syntax, logical language of Hoa logic. And then we get this abstract technique, but the abstract techniques, it is abstract in general, it's got this parameter. And we can get many instances by having different parameters here, such as like one parameter would definitely give us the original technique back. But if we instantiate the parameter differently, then we will get a novel technique that shares the theoretical essence from the original technique because it comes from the same abstract technique. But this novel technique, different instantiation can look wildly different from the original one. And I thought that this line, so this workflow of transferring theory via this abstract layer, it can be used to go beyond the discrete and continuous barrier. Right, and then this is what we are pursuing now still, and it gave us this Erato grant. It gave us, it allowed us to form this project and some sizable team. Yeah, but then once we started working on this project, so like here we emphasized the application to real-world systems, the limitation of formal verification in general became quite obvious to us. That is, so in short, in formal methods and also in control theory, that is, in a sense, our continuous counterpart, safety is a theorem to prove, right? Safety is a theorem to prove. And mathematics is about definitions and theorems. So if we want to prove a theorem, then we need to define all the notions that appear therein. Yeah, but then what are definitions in formal methods? They are white box system models. They're like explaining all the operating principles, how it works internally and so on. And the trouble is that fundamental difficulty is that for most automotive systems or for almost all industry systems, white box models are rare. Now there are two main reasons for that. One is the physical reality is like it's so rich, the interface is so rich that comprehensive modeling is very hard. Another emerging difficulty, source of this uncertainty, is machine learning components. You have probably heard that neural net output behaviors, the behaviors of neural nets, they are highly unstable and unpredictable, and this poses a challenge when we want to model the whole system. Okay. Yeah. So like basically when we want to formally verify cyber physical systems such as automated driving vehicles, like we need to describe such a system in now format that is supported by formal verification techniques, right? Like such as this language. And then, so today in the technical part, I showed you that the continuous dynamics could be modeled by this infinitesimal constant, still using while loops and so on. But these external uncertainties and internal machine learning uncertainties, they are still, like these challenges still remain. So yeah, so therefore, like, these challenges that we encountered when we worked on real-world systems, they forced us this move from model-based techniques to model-free or model-assisted techniques. The bottom line is that we need white box models for end-to-end verification, but these are simply not available in many settings. So in such settings, we inevitably rely on black box testing. So that is like no verification, is like empirical guarantees, right? So, but then, yeah. So this is what we found out, I don't know, like 1 year after we started this project, and probably many of you already knew it. But then the thesis, what we decided on is that the logical reasoning is still useful in such black box analysis. Logical reasoning can empower black box techniques too. And since then, yeah, in the last 3 years or so, we have been doing so in different directions. For example, search-based testing, trying to hit a rare bug, but using logic as a guidance there. Runtime monitoring is another direction. Model learning, combining, I know many of you work on this too. Automata, like model learning in the form of automata, this is something that we can try to do too. And then formal verification, logical deductive verification, but with gradual refinement in a language called event B. It is another direction that we are working on. So yeah, okay. So I'm afraid I don't have time to explain this, but so this is how such stochastic gradient descent based search-based testing, trying like gradually moving to input signals that are more likely to be erroneous. That's gradient descent. How such continuous optimization-based search-based testing can be enhanced with logical constellation. We used this hierarchical framework that was our CAV work. Yeah. So, but in any case, yeah. So, real-world cyber-physical systems, there are no models, so there is no end-to-end verification in many settings. So therefore, we need to rely on black box techniques. But our thesis now is that logical reasoning that we used originally for formal verification, it can also provide a great help to such black box techniques. And I believe this is my own view, but programming language research in the coming 10 years or perhaps longer, it will be centered around this theme of coping with uncertainties, absence of models and so on. So in doing so, we will be combining logic with testing various other fields like testing, software engineering, machine learning, statistics, and so on. And then this, so that this theoretical research can be relevant to practical challenges, and we know that this practical world, the real world, is changing very rapidly
I have quit
nowadays,
now.
Right?
Basically, I was audible the whole time.
Okay,
I have
so
to
then,
sit like a dog.
yeah,
As soon as
I
he
need
makes
2
me a
minutes to
co-host, even
conclude.
if
So
I'm muted,
I
I'm
showed you
audible.
this theory and practice.
I don't understand.
This is an ideal scenario
I mean,
for, I guess, many
This
PL
is, I've
research,
been
right?
searching, there is
We
no
like theory, but
non-bug
we
such
want
as
to
this
make
one. I
practical
was muted
relevance.
the whole
And
time,
there are these
according to
threats.
Zoom.
And
Like everyone could hear
like
me.
my personal lessons, the lessons that I got personally is that, okay,
Yeah,
so
I mean,
these
even
two,
people
for
were
these two
complaining in the chat.
threats, solutions
Just
not
because I was
effective,
clicking,
questions
I'm
not
doing
interesting.
things. So it's really
My
frustrating.
experience tells that
Well, it is.
to overcome such difficulties, theoreticians should dive into the application. So the challenge here is to match theoretical results and applicational problems, right? Then in such a case, I often see this kind of attitude, like so a theoretician saying, give me a theoretical problem, formulate a problem, then I will solve it. And this will never work. And like, quite contrarily, I would say that 70% of theoreticians' work is to formulate problems. Why? Because problem formulation can be only done by theoreticians. It cannot be done by practitioners because theory's power, it mostly comes from abstraction, right? So, but this abstraction is usually only in theoreticians' heads. So, so in other words, it is very hard for practitioners to know the whole picture of the theoretical results. So they cannot find such matching. It's just that theoreticians with this abstract knowledge, they have to dive into the application, know concrete challenges, and then make matching like this from abstract general knowledge to concrete instances. And this can be done only by someone with this abstract knowledge. Okay, and then there is this another challenge of communication barrier. And the lesson that I got from my experience is that we need to explore formally and informally. Like, yeah, interdisciplinary collaboration is usually hard, right? Different languages, different cultures, and but the specific challenge here is to communicate tacit knowledge. So when two people talk to each other, like explicit knowledge, that is the knowledge that Alice knows she is using. This can be communicated, but the problem is this tacit knowledge, that is the knowledge that Alice is using, but Alice doesn't know that she's using it. And usually this is the most important knowledge. And like one example is that like if you work in a field, there are some goals and values shared by the people working in the field, right? For example, in programming language theory, we like soundness theorems, yeah, right? But then so this kind of, we need soundness theorem, this kind of goals and values, you don't say it when you talk to somebody else. So and you even don't know that you are using this knowledge, right? So it's very hard to communicate this tacit knowledge to others. And well, probably the only way to do so is to explore. Like this was an advice by Pete Hutt, a specialist, professional in interdisciplinary collaboration. So exploration can include casual chat over walks, casual chat over coffee, casual chat over drinks, like casual chat, like in a sense, stupid chat. These kind of like exploration in communication is probably the only countermeasure here. And another thing is meeting the right person solves many problems, and it was Kohei to me. Yeah, and then finally, like to do this, we theoreticians, we need to be collaborative, and I was not before, and I mean, there's a tendency that people are less so in theory, I believe, but to be a collaborative researcher, one thing that I learned is that we need to be a good listener. So this is from my experience of hiring many researchers, and many among them are meant to be collaborative theoreticians. And like these are the people, some of the people that some of the people among them. And then what I learned from them is that we need to listen well, and we need to try to build on others' ideas. Yeah. Okay. So. Yeah, this is to conclude. We want such an upward spiral, and I had a technical part about this specific line of work, and then, but so this was about formal verification, but to be relevant for real-world cyber-physical systems, we probably need to move from model-based to model-free or model-assisted, but still the power of logic is there. And like, yeah, we need to cope with uncertainties. And then there are some, like I would say, practical tips that I learned from my experience about making this upward spiral realize. Okay, this is it. Thanks a lot for your attention.
Thank you for your talk, Ichiro. Then, any question or comment?
Thanks.
It's part of the recording, I think. Yes. As your colleague said, thanks a lot for your talk. I know we're dealing with some kind of Zoom issues with people muting and unmuting. I'm really sorry. I'm trying to kind of mute people, but there's some weird technical difficulties. Sorry, I think most of the talk was still audible, but we're kind of handling this for the first time. Are there any questions that people would like to ask Ichiro? You can either type in the chat, or if you raise hand here, I can try to have you unmute yourself and ask the question. Trying to monitor the chat. Okay, so I think I'll ask one question that kind of came up to me, because I'm also someone who kind of tries to work more theoretical and try to connect it to practice sometimes, but it seems kind of difficult. Do you have any advice for kind of, finding people to talk to who have more kind of practical concerns? Like where do you find people who are able to kind of talk to people doing theoretical PL and also have an idea of kind of the practical concerns that might be solved by these problems? So you said your colleague Kohei Suenaga kind of brought many of these works to you, but I was wondering if you had any thoughts on that.
Okay, so again, like my experience is very limited, but like one thing is that there, like in this field of programming languages, people sometimes go to industry and then come back, right? And then so like those people, they tend to know about both worlds, academic research and practice, theory and practice, right? So that's one way. And another way is that we have got a bunch of graduates from our fields, from our departments, like, computer science, programming language, PhDs, masters, working in many branches of industry. And for example, my experience is that when I give a presentation, like one practical tip is like when I give a presentation to the industry audience, I intentionally try to include one hardcore theoretical stuff. Then this usually rolls out those theory-oriented ex-computer scientists, ex-computer science students, and then they come to talk to us. So that can be a practical tip. Thanks, Justin.
Cool. Thanks a lot. Are there any other questions? Zaley has a question.
I just wanted to say there are a couple of questions on Clouder. Hopefully everyone can hear me, so I'm happy to read them out. Sanjeeva Prasad is asking, I'm curious to know the state of the art of decision procedures for non-standard logic.
Okay, so I have to say, like this non-standard analysis work I did quite some time ago, and I'm not the specialist. I was like let's say I was a user of it. But then since we have got this transfer principle, I would say it's the same as the state of the art for the usual first order logic for real numbers. That is, and then there's this Tarski's theorem that is decidable, right, with quantifier elimination and so on. But then when it comes to practical problems, I mean, like for example, practical decision problems, whether this given formula is valid or not. So we typically use quantifier elimination algorithms, CAD and so on, we used Mathematica, and QE is heavy. Like for a formula that is a bit complicated, it's impractical. So I hope I answered your question, Sanjeeva. Thanks a lot for your question.
Yeah, there was a correction. They meant to say non-standard reals rather than non-standard logic, but I think the answer was perfectly sufficient. And there's another question we have from Gabrielle, who asks, you created a sizable group. How did it work to hire many people and try to collaborate with them?
Yeah, thanks a lot. Again, like I started doing this a few years ago, and like there are people with like years of experience, years of such experience, right? So I feel very humble saying this, but okay. So this is when I started to form the group, I talked to my supervisor, Bart Jacobs, and then his tip was that get like a couple of core people that I can trust. So then, like once, so he said, once you get a few core people, then the rest will follow. And I think that worked. It worked that way. And these core people consisted of Kohei and some other, like one software engineering specialist, and then one category theorist. So it was, this core people was already quite a weird combination, like programming language guy and category theory guy and software engineering guy talking to each other. But then, like to kick off this collaboration, we started out with informal exploration that was basically a camp talks, and then drinking and eating, and chatting. I hope it's useful. Thanks a lot.
Thank you very much. I actually have a question myself, unless there are other questions from the audience. You could remember you could post them on Clouder, you could raise your hands in Zoom, and Justin can unmute you. Any of these techniques work. But in the meantime, so I'm personally, I've always worked in theory, being my PhD, and then later on, and recently I've started getting to practice, and I'm collaborating with a bunch of people who are essentially engineers. And one of the difficulties of bottlenecks of this collaboration has been fantastic, but one of the bottlenecks is writing up. We have very different techniques and very different audiences. Forget about deciding the value, even just the method of writing up the result is quite difficult because we are, by nature, catering to different audiences. So do you have any advice in that? How did you reconcile the two worlds?
Yeah, again, I'm definitely not the best person to answer to this, but I think once you have experience in 2 different fields, then the third, fourth, they will be easier. So like, yeah, like 1 and 2 or more, yeah. And there's a big barrier there, but yeah. So like it will be easy, I guess. Hopefully, yeah.
Are there any other questions?
All right, I don't see any more questions in Clouder. I think.
There are lots of comments, but
yes, lots of comments, but no questions. All right, so let's all thank Ichiro Hasuo one more time. Have the clapping emoji. Thanks for the great talk. I think this is a really interesting, perspective, and it's a very timely perspective as well. So thanks for making this talk and kind of being here with us at PLMW.
Thank you so much, Ichiro.
Thanks, and so sorry again for the noise, right? It was like many of them were in the original recording. Sorry about that. Yeah, thanks.
It's okay, no problem. All right, cool. So I think the next talk is going to be at the top of the hour, so about 40 minutes. But until then, I think Gabriel, if you're around, Gabriel has planned maybe some kind of informal social event or some kind of student roundtable. Gabriel, can you hear me?
Yep. Can you hear me?
Yes, we can hear you.
Yes. Yeah, okay.
I'm going to make you host, actually, if that's okay. Okay, so just, yep,
yes,
sounds good.
So, yes, so my idea was, I think we were a bit worried when we started organizing that with half an hour of a break, people would just start reading the email and disappear, and we would never see them at PLMW again. So we had to find a way to get people interested in staying until the next talk. The suggestion was to do a round table. So let people introduce themselves if they want to, except that there is like 100 of us. So we will not have time to do an actual round table of everyone. But I was thinking maybe would